Rectilinear motion is continuous motion in one dimension. It's often referred to as kinematics in one dimension. We want to start by defining a couple of different values in rectilinear motion. The first of those is position. Some books will use the letter S for position, and some books will use the letter X for position. S generally stems from a discussion of arc length. You may recall from geometry some years ago, whenever you had geometry, that the arc length of a portion of a circle, S, is equal to the radius of that circle times the angle theta measured in radians. And so that's kind of where the S is coming from. But for the most part, I'm going to discuss position using the letter X. Displacement is a change in position. And so we use the Greek letter delta to indicate change. So a change in position would then be delta x. All right, now that's going to be defined as a final position minus an initial position. Sometimes we could write this as x2 minus x1. And that would be movement along a number line. So you might start off at x equal to 5 and end up at x equal to 17. In that scenario, your change in position would be 17 minus 5, which would be a change in position of 12. Now notice that we could have started off at 0 and ended up at 12, and then I'd have 12 minus 0, which would also be 12. So a change in position does not necessarily mean position. You shouldn't confuse those two categories. A change in position is how you start versus how you finish. And it could be the same even though two changes in position are not from the same locations. So keep that in mind. Velocity, by definition, is going to be, well, we're going to define it in two different ways. We're going to start off with an average velocity. So an average velocity, which I'll subscript with an AVE for average, is equal to a change in position with respect to time. And that's actually a definition. So I'm going to use 3 bars in my equal sign instead of 2. This is how I define the average velocity. So one thing to keep in mind here, as I'm talking about an average velocity, that doesn't mean I'm moving or not moving necessarily. For example, if I start on the right-hand side of the room, I walk across to the left-hand side of the room, and I return to the right-hand side of the room. That's going to take some time, and I am moving that whole time. My average velocity is 0 because I started at some position on the right-hand side of the room. I ended up at the same position. My change in position, even though I moved, is 0 because I started where I ended up. So don't confuse velocity with speed. They are not the same thing. Yes, there is a relationship between the two, but they are not identical. In a similar fashion, we have an instantaneous velocity. An instantaneous velocity, which I'll just write as a v, is defined as the derivative of position with respect to time. And so in my previous example, as I'm moving across the room from the right side of the room to the left side of the room, my velocity has some non-zero value because I am moving. And in fact, if we think about positive to the right and negative to the left, I have a negative velocity. Now, that doesn't mean I have a negative position. They are not the same thing. So if I start my number line at the left side of the room and I start at the right side of the room, I have a positive position the whole time I'm moving to the left, but I have a negative velocity. And then at some point in time I have to turn around, so my velocity is changing. We'll talk about that in a moment. And I head back to the right-hand side of the room, and I end up moving to the right, so now I have a positive velocity as I move back to my original position. These velocities do not need to be the same. I could walk to the left side of the room and run to the right side of the room. So don't think about an average velocity as the sum of those two values. For example, I could be moving to the left side of the room at -2 meters per second. And then I would move to the right side of the room walking at 1 meter per second. Now, if we average these two values, -2 plus 1, and we divide by the two values, that is equal to -1/2. So that's not my average velocity. My average velocity is 0 because I started off at the right-hand side of the room. I ended up at the right-hand side of the room. So be very careful about this concept of average velocity. It's not the average that we talked about, let's say if we're talking about quiz scores. If there's 10 of you in class and I take the 10 quiz scores and I add them up and I divide by 10, that's the average quiz score. Average velocity is not defined the same way. It is not defined the same way. That's the difference between continuous mathematics, or in the case of the quiz scores, what we call discrete mathematics, because there's individual values for each quiz. They're not along a continuum. They're discrete. Okay, that's very different. Not going to get into that math theory at this point, but definitely do not confuse those two things. All right, so now let's talk about acceleration. Acceleration is going to be defined as a change in velocity with respect to time. So the average acceleration is equal to, and defined as, so 3 bars now, the change in velocity with respect to time. The change in velocity with respect to time. So if we think about the movement from me going from the right side of the room to the left side of the room, what did we talk about? We said I was moving to the left at -2 meters per second, and then I had to turn around and move to the right, and now I'm moving to the right at 1 meter per second. So my change in velocity would be 1 meter per second. That's the final velocity, minus a -2 meters per second. And then how long did that take? Well, I don't know. Let's say it took 1 second. And so what I find is that I have 3 meters per second. That's my change in velocity. Direction matters. Okay, my change in speed is from 1 meter per second to 2 meters per second. Actually, the other way around. So the change in speed is different than the change in velocity. And then I divide that by 1 second. And we'll worry about the units here in just a minute. The instantaneous acceleration, A, is defined as the derivative of velocity with respect to time. Now, these are definitions, and this is critically important. No matter what I tell you about the functions, are they functions of time? Are they functions of position? Are they functions of velocity? Whatever. Doesn't matter. These definitions always hold true. We'll get into that in much more detail here in just a little bit. These definitions always hold true. All right, so let's talk about the dimensions or the units. Now for position is defined as having dimensions of length. So in the English system, this might be in feet. In the metric system, this would be in meters. Velocity, on the other hand, if we go back to the definition of velocity, that's the derivative of position with respect to time. dx is a change in position, and a change in position is going to have dimensions of length. A change in time is going to have dimensions of time. And so velocity is measured in length per unit time. And so in the English system, that would be feet per second, and in the metric system, that would be meters per second. Of course, we could have inches per second or kilometers per hour. All of these are also units of velocity. But the interesting one is acceleration. Keep in mind, acceleration is defined as a change in velocity, a derivative of velocity, if you will, with respect to time. Now, velocity is in length per unit time, and then I'm dividing that by time. So that's length per unit time divided by time, which is length per unit time times 1/time. That's length per time squared. Length per time squared. And so in the English system, that would be feet per second squared, and in the metric system, meters per second squared. Other possibilities also exist. I could have miles per hour per second, or miles per hour per minute, something like that. But one of the units that I really like is meters per second per second. And the reason I like that is it's telling you that Meters per second is a speed or a velocity per second. So there's a change in that velocity with respect to time. And that's the critical value of acceleration. Acceleration is not velocity. If I'm traveling at 70 miles an hour and I slow down to 60 miles per hour and I do that in 5 seconds, that's 10 miles per hour per 5 seconds, or 2 miles per hour per second. All right, so again, I'm going from 60 miles per hour down to, or I started at 70 miles per hour. I went down to 60 miles per hour and I did it in 5 seconds. So that's minus 10 miles per hour per second. That's an acceleration. That's the same acceleration as if I go from 20 miles per hour down to 10 miles per hour. And I do that in 5 seconds. It's the same acceleration. They're the same. They're both minus 10 miles per hour per second. Not the same velocity. They are not the same velocity. So acceleration is a measure of how fast changes. How quickly do you change your speed or velocity? This is what they use when they're rating cars. They'll say a car goes from 0 to 60 in 3 seconds. That tells you you have a lot of acceleration. That's an important issue. I have a car that would go from 0 to 60 in maybe 10 seconds. They're both going to make it to 60 miles per hour. One of them makes it to 60 miles per hour in a shorter time period than the other. So the units are not the same. Acceleration is not velocity. Yes, they're related, but they are not the same thing. All right, so let's assume that I have position, and position is a function of time. So there's my function notation from mathematics way back when you were in algebra. This is a function notation. Position is a function of time. And so velocity is equal to the derivative of position with respect to time. But let's do this. Let's multiply both sides by dt. All right. So the left side becomes v dt, and the right side becomes dx. And then let's integrate both sides. And what I have on the right-hand side, let's integrate from x1 to x2. This becomes x2 minus x1, or a change in position. A change in position. The left-hand side, I'm going to integrate. Now, notice the operator, or the variable of integration, is time. So there's going to be a time associated with x1. Well, that's going to be some time t1. And there's going to be a time associated with x2, and that's going to be t2. So your limits of integration have to correspond to each other. They aren't the same, because one's a position and one's a time, but they have to correspond. The lower limit on one integral has to occur simultaneously with the lower limit of the other integral. Similarly, the upper limit of one integral has to occur simultaneously with the upper limit of the other integral. What is the integral of v dt? I don't know. It depends on what the velocity is. What is that velocity, which is also going to be a function of time. All right, but what do I know? Since velocity is a function of time, then if I were to integrate time here and velocity here, and I have some function in here, then the integral of v dt, measured, say, from t1 to t2, that's going to be the area underneath this graph. And so the area underneath that graph is the change in position. The area underneath the graph is the change in position. What's the slope of the graph? The slope on the graph, if this is a velocity versus time graph, the slope is the derivative of velocity with respect to time. Well, that's the acceleration by definition. So the slope at any point is the acceleration. Well, notice the acceleration where I've drawn it here, that's going to have one value. But the acceleration over here, that's a different value altogether. And so in this particular velocity versus time curve, the acceleration is changing. Okay, so acceleration does not need to be constant.